Hi, my name is Zach Lassiter, and today I'm going to give a brief lesson on combinatorics and other basic counting principles. First, I'm going to talk about permutations. So permutations are fundamentally the number of ways to choose and order a number of objects in a given set. Some key points to remember about permutations are order matters. It's denoted as p parentheses n comma k and read as k permutation on n objects. Additionally, it always equals n factorial when n equals k, and we'll see why that is later in the presentation. To go over the concept of permutations, we're going to just discuss a simple problem where n equals k. In other words, we want to know how many ways can we order n objects. And here's our guiding problem. So Northeastern is putting on an end-of-semester parade that will march through campus. 6 clubs have been assigned to manage their own exhibit in the parade. Jake, the parade coordinator, is discussing the order of the exhibits with his friend. How many different parade orders are possible? Now, to go about solving this, we can best intuitively reason through it using the multiplication principle. So for our problem, each of these lines represents the order of the parade. So here's our first position in the parade. So you can see for this, the first position, we have 6 options. And after that, obviously, we have 5 options, and so on and so forth. So we can see that to order 6 objects and these 6 exhibits in the parade, we have 6 factorial. So we can see that when n equals k, a k permutation on n equals n factorial. And in other words, the number of ways to order n objects is n factorial. So how about when k does not equal 0? So we can consider our same situation with the parade, but let's say now Jake must choose only 3 of the 6 clubs to parade around Northeastern. So now we are looking for the 3 permutation on 6 objects. So again, we have our order. For the first position, we have 6 different options, and the next we have 5, and then 4. So our final answer for the 3 permutation on 6 objects and the number of parades, permutations of 3 parades of 6 clubs is 6 times 4 times or 6 times 5 times 4, or 120. Alternatively, if Jake was told to choose 7 of the 6 clubs to participate in the parade, or if k was greater than n, then 0 arrangements are possible. This is fairly intuitive, but it is also an important thing to remember. Now, let's talk about the permutation formula. So here we have our k permutation on n, and we can see that that's equivalent to n factorial over n minus k factorial. If we plug that in to our problem, we have that the 3 permutation of 6 is 6 factorial over 3 factorial, or this big long thing, which you can see this just cancels out to 6 times 5 times 4, which is what we got when we were reasoning it out using the multiplication principle. Alright, now let's talk about combinations. So combinations are the number of groupings from a given set of objects. Some key ideas to remember about combinations are order does not matter. It is denoted like this, and read as n choose k. Since order does not matter, there will always be, well, for the most part, always be fewer combinations than permutations. To touch on this subject, we're going to consider an example problem. So consider a school-wide high school dodgeball tournament. Each homeroom must enter a team of 8 students to compete and represent their class. How many unique teams can the class possibly put together if their homeroom has 20 students in it? So we can see that order does not matter here, and this is clearly a combinations problem. So here's one example of a combination. Here's our class of 20 unique students, and you can see that we're just selecting 8 out of the 20 to represent one team, and order does not matter. So how do we go about solving this? Well, let's first consider it from the standpoint of permutations. So if we consider the 8 permutation on 20, we said earlier that the number of combinations is, for the most part, always fewer than the number of permutations. So by how much are we overcounting? So in our set containing all the permutations of different teams, Each team combination appears as many times as there are different orderings of 8 objects. So earlier we concluded that k objects can be ordered in k factorial ways. Thus, we are overcounting by 8 factorial permutations per valid combination. So now if we try to derive a formula, it follows that n choose k equals the k permutation on n divided by k factorial. And if we just extrapolate that, we get n factorial over k factorial times n minus k factorial to be our formula for n choose k. So if we plug in our numbers from our problem, we get that 20 choose 8 equals 20 factorial over 8 factorial times 12 factorial possible teams. And we'll see that that number is much less than the number of valid permutations, the 8 permutation on 20. Alright, now I'm going to go into some more detail on some different niche counting concepts. Alright, so say we wanted to count the number of arrangements of n objects, but with one or more of the elements repeating themselves. An example of this would be how many ways can we rearrange the letters in Mississippi. Alright, as you can see, there's a few repeating letters. The I repeats 4, S4, P twice. So at first glance you might think, okay, there's 11 letters, so 11 factorial, since we just want to count the arrangements of 11 letters. However, we're overcounting here. The reason for that is there are several letters that occur multiple times, and since those letters repeat, the order at which they occur in the arrangement does not matter. For instance, if you just swapped 2 of the S's, it would be the same arrangement. Alright, so as I said before, I occurs 4 times, S 4 times, P 2 times. So therefore our final answer will be 11 factorial over 4 factorial times 4 factorial times 2 factorial. And here we're just dividing out the number of ways to order the S's, the number of ways to order the P's, and the number of ways to, the number of ways to order the S's, the number of ways to order the I's, and the number of ways to order the P's. This is commonly referred to as the bookkeeper rule. Next, I'm going to go over balls and bins problems. So what if we wanted to distribute n objects into k-labeled categories? For example, Max is going on a week-long vacation. He wants to bring pants to wear for 7 days. The types of pants he could bring include jeans, khakis, sweatpants, and shorts. How many different ways can Max pack pants for his vacation? How would we go about solving this? Oops. So here we can see this is just a little visualization of our problem. So here are our 4 categories. We could, for instance, make one day he brings 1 pair of jeans, 1 pair of khakis, 1 pair of shorts, 1 pair of sweatpants. That's 4 days. And say he brings 2 pairs of jeans and it's warm, so he'll bring another pair of sweatpants. He'll bring 2 pairs of sweatpants, and then we have 3, 4, 5, 6, 7. All right. But it could just as well be all jeans, all shorts, all sweatpants, whatever. And we would just want to count how many different possibilities are there. For instance, he could also, do this 1, 2, 3, 4, 5, 6, and then 7. That's also a valid arrangement. And we just want to count all those arrangements. So. Alright, so one way we can do this is we can represent the different ways of packing as binary strings. For example, 0, 1, 0, 0, 1, 0, 0, 0, 1, 0 would be valid. Each way of packing is a binary string where the number of digits in the binary strings equals the balls plus the bins minus 1. And in this case, that is 7 plus 4 minus 1. So a 10-digit binary string. And that just represents the total number of digits, where this is one of those bars in the category, so is this, and so is this. So everything here, this would be the number of jeans, 1 pair of jeans, 2 pairs of khakis, 3 pairs of shorts, and 1 pair of sweatpants. And essentially what we want to do is find all of the different ways we can choose where the ones are in this 10-digit binary string. So we have 10 digits and we want to choose 3. And that will give us all of the different ways that Max can pack for his trip. Alright, now I'm going to go over one final counting problem example. Here's our question. A class has 14 girls and 10 boys. How many different groupings can be made of 3 girls and 2 boys? So how will we approach this? We'll tackle this in 2 steps. First, we want the number of ways to choose 2 boys. So since there are 10 boys total in the class, we'll take 10 choose 2, which comes out to 45 different ways. Next, we want the number of ways to choose 3 girls from 14. So 14 choose 3, that gives us 364 ways. Thus, our final answer will be 45 times 364 total unique groupings. Thank you all for watching. Have fun counting.